Let's begin the second part of the intermediate course on the fundamentals of noise. To begin, let's discuss the effective use of EMI/EMC filter wiring and placement. Ideally, EMI/EMC filters should be wired so that input and output lines are far apart. If the input and output lines are close together, noise on the output line side may affect the input line side, and the expected effect may not be obtained. Next is an example of the impact from noise by the placement of EMI/EMC filters. I has an EMI/EMC filter installed far away from the switch mode power supply, which is a noise source, to achieve a high attenuation effect. In case B, the input line of the EMI/EMC filter is installed near the switch mode power supply, so the magnetic flux generated by the switch mode power supply couples with the input line, resulting in an increase in the noise level. If the location where the input line arrangement of the EMI/EMC filter is installed cannot be changed, it may be possible to take countermeasures by attaching a metal cover to the switch mode power supply that is the noise source, as shown in C. Shielding the switch mode power supply prevents magnetic flux from jumping to the input line. Magnetic field noise is mainly generated from transformers and chokes, and a magnetic field that is synchronized with the switching frequency is generated. This magnetic field may affect ICs and other devices directly magnetically, or the magnetic field noise generated by electromagnetic induction may affect ICs and other devices as motorized noise. In the case of an open-type power supply, the magnetic flux generated by the transformer and choke may become motorized noise when linked to the peripheral circuits. In the case of metal case products, magnetic flux generated from transformers and chokes is consumed by the metal case as eddy currents, reducing magnetic field noise. This reduces the impact on peripheral circuits and prevents malfunctions. Next, I'll explain transmission by electric field. Electric field noise is generated by switching elements and circuit patterns with high voltage amplitudes. For example, the inverter voltage amplitude of a DC-DC converter with 24 V DC output is approximately 70 volts, and the electric field noise is transmitted through the capacitance of the source components. However, electric field noise can be reduced by connecting the metal case and circuit patterns to a stable potential. In this section, I will describe the grounding wiring of the EMI/EMC filter. If the ground wire is long or thin, the inductance component of the wiring may affect the expected attenuation properties over a wide area, so it is better to wire the ground wire of the EMI/EMC filter as thick and short as possible. Connecting the metal chassis of the EMI/EMC filter directly to your chassis will have the same effect as if the ground wiring was thicker and shorter. Herein, I will explain the orientation of the EMI/EMC filter and the effect of combinations. The EMI/EMC filter has a line and a load, but it can be connected in the reverse orientation without problems. Depending on the impedance of the equipment, connecting the EMI/EMC filter in the reverse orientation may be effective. A typical EMI/EMC filter is a low-pass filter configuration that combines L and C. The optimal EMI/EMC filter circuit configuration depends on the input impedance on the input side and the impedance of the device. If the desired attenuation effect is not obtained, the input impedance or the impedance of the device may be affected. Additionally, two EMI/EMC filters can be used in series. Two single-stage filters can be used in series for an effect similar to that of a two-stage filter. However, care must be taken because increasing the number of EMI/EMC filters used will increase leakage current. If two units of the same EMI/EMC filter are used, the leakage current will be doubled. Even when two EMI/EMC filters are used in series, it is necessary to consider the orientation and combination of EMI/EMC filters. When two EMI/EMC filters are used in series, the typical connection method is to configure them as T-type filters as shown in connection example 5, since the maximum effect may not be achieved depending on the orientation or combination of the filters. Now let's talk about how to deal with external impulse noise. External impulse noise refers to noise generated when motor loads and high-power devices are switched. Impulse noise is characterized by short pulse widths and high voltages, and may cause malfunctions if it enters control equipment. To dampen this noise, a filter with a built-in core suitable for the purpose of the countermeasures is required. In the case of impulse noise entering from an external source, countermeasures using a standard EMI/EMC filter with a ferrite core may not have the expected effect. Standard EMI/EMC filters with ferrite cores have a low saturation flux density and may saturate, while EMI/EMC filters with amorphous cores have a higher saturation flux density than those with ferrite cores and can therefore dampen high impulse noise. This makes it effective in preventing equipment malfunction. This concludes the second part of the intermediate course on the fundamentals of noise. Thank you for watching.